Continue with opal, and we're going to move on to color and optics, the gemology portion of the lecture. Well, I want to first talk about our cause of color. Why does precious opal have such a beautiful play of color that we see here in this bolder opal and in this black opal going from blue to green? Cherry opal has a brilliant red. We can talk about all these different causes of color. All right, so here we go. We finished talking about the formation processes of opal, and that leaves us now with two main things to go into, which are going to be the gemology, which is our color and optics, and then of course we'll finish with sources. The most important thing we should talk about here is, why do we get the color that we have? So this is going to be the color, and I'm not talking about the color of the background. That's from the type of rock most of the time. This is the color of the flash, right? And it's that which is making all of the value for opal. So here's what we're going to do. We're going to go here. This is going to be cause. And real quick, we're going to just write down, I know we've talked about this earlier in the semester, the cause is diffraction of white light by close packed structured spheres. Diffraction of white light, that's the incoming light, by close packed structured spheres. In terms of physics, we're producing a diffraction grating like the back of a CD. So let's just say, like example, it produces this situation which is a diffraction grating like a CD, and it causes this beautiful rainbow to our eyes. The color that we're seeing is kind of neat. It has to do with the size of the sphere. So what I want to say here is that the colored light that we see is 2 times, or the wavelength is 2 times the size of the sphere. So if we had, how do we say this? Let's say if we had spheres, 300 nanometer diameter spheres, they're going to produce a 600 nanometer wavelength of light. And then if we looked at the rainbow, what is 600 nanometers? Well, 600 nanometers is orange light. This is why we see the color. It's all about the size of the spheres. So blue and violets and greens, those are smaller spheres. Bigger spheres, like 300, 350, they're making oranges and reds. So how do we say this? Let's say colored light is 2x sphere size. That would be kind of a good reminder for what we just did in that example. And that bumpy surface is, so we can draw it, I guess. Here's our layer of 300 nanometer diameter spheres. That ends up producing our diffraction grating that returns light to our eyes. Now, how does this relate to value? Well, size relates to value because red is the most valuable color of flash. It's also the rarest. And the reason why it is so valuable and also so rare is because it requires spheres that are 310 to 370 nanometers diameter. And those spheres are big, and it's harder to grow bigger spheres. So let's just say is that it is harder to grow big spheres. And that makes red the most coveted color. Orange would be the second. It's kind of like an inverse rainbow, right? An inverse rainbow. So as you go Roy G. Biv, this is the cheapest. And our reds and oranges and yellows, although not so much yellow, these are our biggest money up here. Now, there's, of course, one other color that matters, and that is when you have common opal that does not have a flash but still is beautiful. So let's just, what is this? This is 2. We're going to call this colored common opal. our best example of colored common opal is fire opal from Mexico. I showed you that cherry example. This is our red to orange, and this is colored by iron oxide inclusions. Iron oxide stain, let's just call it that. Other colors are possible too. There's beautiful blues coming out of Peru. There are pinks. There's all these other hues that can have value if the common opal is satisfying to our eye. And I guess there is one third type, and this is a color type called contraluz, which is coming from Spanish. I guess it means against the light. And most of the time we see opal color. So if here's our opal, we see the color because light is diffracting off of it. And so we'd call it like a reflectance. There's our eyeball here with our, there's our eyelashes. We have eyelashes, is that? We'll just call that eye. That sketch is starting to look a little wonky. But a contraluz, this is the color of transmission. If it's a really clear opal, then you can sometimes see light coming through it, and that can have value at times. Now, another aspect that matters to the gemology is the texture of the opal. So let's go to texture, and this is going to be how big let's draw 3 cabbage. Oh, that's a terrible oval. I want you to draw 3 perfect ovals. I'm going to try to get better. Okay, there's our ovals. We've made beautiful cabochons. There can be, so the texture is the coarseness of our play of color. And there's 3 different types. One type is called pin fire. Pin fire is very, very fine grained. You get all these really small flashes of color. Actually, I could do that, couldn't I? I could put reds and blues and greens throughout, right? But they're all really small. This is called pin fire. It is our lowest value texture. The second, well, then these other 2, these are both higher value, and the flash is when you have really large sectors of color. Okay, we'll go flash. You get the idea, right? These are big sector zones. And the bigger they are, we'll say this, bigger zones equals more value. And then the last texture type that matters is called harlequin. And this is a slightly strange. They are large sectors of color that are polygonal. They're like interlocking rectangles. So let's just say large, polygonal, interlocking texture. It actually starts to look man-made. How can we draw this? We basically want to just draw a bunch of different colored squares. Right? Where flash also was big, but they were more irregularly shaped, but not so with harlequin. Harlequin is very regular in the color zoning. All right, so those are our 3 main types of textures, where these 2 are going to be worth the money, and these are just to be ones that we can afford unless we're like super filthy rich. And then now let's just let's end this thing with a little bit of talk about the sources for opal throughout the world. Sources for opal. And in fact, I'm going to go ahead and just put the map up from GIA. This shows where in the world opals come from. We'll only talk about a couple of the regions. The Romans would get their opal from here when it was such a popular stone back in their era. But nowadays, about 90% of opal comes from here in Eastern Australia, in New South Wales and in Queensland. Both black white and boulder opal all come, well, I guess there's another area right about here in Australia. So this is about 90% of the world's opal, at least until the last few years when Ethiopia really started to come online. And now Ethiopia is massively growing as a producer of white opal and crystal opal. In the United States, we have a source as well in Nevada. It's a place sometimes you can even go mine as a tourist to see if you can find your own opal. And there's other places around the world too. I guess we should do one thing. We should circle this one in Mexico because we'll talk about that. That's where the majority of the world's fire opal comes from. So let's just do a couple notes about these different locations. Let's start with Australia. One of the neat things about Australia for opal formation is that much of Australia is this huge desert, and it's a low-lying sedimentary basin. And so it's that perfect environment to get a lot of precipitation and then drought with evaporation. So let's say low-lying sedimentary basins rich in silica and is desert, and has probably been desert for the last tens of millions of years. So we can think that this is going to have a lot of water, a lot of drought, and giving us that perfect environment to produce opal. The most famous areas in Australia for opal, probably the most famous, is called Lightning Ridge. And Lightning Ridge is the world's source for black opal, that most precious, most expensive variety of opal. It occurs in these really clayey nodules around 6 to 18 meters underground. So people are digging tunnels underground to find these nodules in the clay, and they're bringing them to the Earth's surface. This is kind of the area in Australia where the black opals are coming from. White opals come from this more middle area. So there's also a large geographic region for white opal. Let's go down to Ethiopia, this growing field of opal, Ethiopia, you think of Ethiopia, you also have a lot of desert. So let's say Ethiopia. Here we have, these are opals that are forming. Opals form in open spaces in rhyolite lavas. Like maybe it used to be some bubble that was in the rhyolite lava that then gets precipitated and filled full of opal. And what we were going to say about Ethiopia is it's starting to take away Australia's dominance on the opal market, and it's making prices go down. One of the problems with Ethiopian opals, there's a whole wide range of quality from very high quality to very low, but one of the problems with a lot of the opals is that they craze. And craze is a bad thing. What crazing means is when you get this fine network of cracks, kind of like spiders' webs, fine networks of cracks that pervade through opal if it dries out. And so what ends up happening is that the Ethiopian opals are very rich in water, and if you do not keep them in a watery, humid type environment, they're going to lose that water and they're going to craze. And so you might buy this beautiful, stunning opal that then just cracks up and is complete, and it cannot be fixed. Once it happens, it's over. So this is one of the problems people are experiencing with Ethiopian opals. They're coming from an area called, well, technically it's called Wolo, but in the market we either call them Wellos or we call them Wello. If you ever see Wello opal, that is an Ethiopian opal. And then I guess finally, let's just talk about the Mexican fire opals. These are the red to orange. They've been mined in Mexico for 200 years. and they've been known for a very long time. They sometimes, so let's say this, let's say they rarely have play of color. Most of the time they're just common opal that has a beautiful shade. And the reason why they rarely have a play of color is because instead of forming spheres, the silica makes platelets. Silica makes platelets. So it's a different shape that gets stacked upon one another. Right? So they get these little plates that all start stacking up on one another. And so you don't get the same kind of diffraction of light. And you just get, I guess you just get kind of everything bouncing back to your eye, not just one single color. That's the story with Mexican opals. Oh, and they're also forming in gas cavities in lavas. Let's just put that down as a source, as our last thing for opals. Gas cavities in opals. And there you have it. That's everything you need to know about opal. See you next time.